and I wanted to talk about how traditional methods and materials, namely mass wall masonry, can play a role in creating a more beautiful and durable architectural legacy here in the United States. But first, I'd like to start off with a few observations. You know, Americans love to travel, including myself, and we're willing to spend thousands of dollars just to experience beauty in another part of the world, even for just a week. And many of these places are not untouched wilderness, but are, you know, cities and towns and neighborhoods, places created by humans, and are some of the most beautiful places on earth. Yet, when we come home, we simply accept the world around us, the suburban neighborhood without trees, the sort of strip malls and parking lots and massive highway intersections the size of small cities. And it just seems normal to us, or at least such a seemingly insurmountable problem that it's hard to know where to even start or, you know, to go about changing it. But to me, I think that requires going back to the why. Why do we build? What is architecture for? To me, the answer to that question is simple. We are building for humans. We build in order to create a flourishing world, a thriving world, a world full of beauty and harmony and stewardship. And yes, there are many variables and constituents involved in architecture, but ultimately, you know, we're not building for banks or building codes or governments or GDP, we're building for people. And that is our inspiration and our cause. And I think it's extremely difficult to keep that in mind in our profession because just about everything out there seems to pull us in a different direction. And you can see the outcome of having lost sight of the why. In the United States in particular, I think we tend to think of any building and development as a destructive force rather than a regenerative one, something that can enrich the world around us. We think that way for a lot of good reason, to be honest, based on what we've been building over the past century. We tend to think of buildings and development as destructive forces, and to me, part of the problem is, this is actually a really interesting slide of, you know, just seeing the example in terms of scale of Sienna, you know, overlaid over a highway intersection from Houston, which is actually where I'm from. But to me, part of the problem is that in the United States, we tend to think of buildings so individualistically, as if the building itself is everything that matters. But like a mosaic, buildings interact with other buildings, and they work together. And at least have done well to frame and create other meaningful spaces, the spaces between the civic realm, and you can see the difference on the caption on the left and then the right of a typical suburban neighborhood with cul-de-sacs and an old European city where you got the negatives of all these spaces that these buildings create. Now, thankfully, the new urbanist movement, really starting with Seaside, has brought a ton of attention to this way of thinking. Have been true pioneers, treating our neighborhoods and towns and cities as complex ecosystems made up of individual pieces that interact with each other, as well as bringing attention to human-centered design. And over the past 40 years, that philosophy has been making its way back into governments and municipalities and academia and even into mainstream thinking. So as that fight continues, and we still have a long ways to go, I'd also like to draw attention to another aspect of architecture that is essential if we want to build great towns and cities and neighborhoods again, and that is beauty and durability. So I just want to share a little bit about my work, but first I want to give a little bit of background of who I am. So I started off actually as a CPA in Houston at a large accounting firm about a decade ago, and not being super satisfied with that, I left and explored and went to Panama, which is where I was first introduced to new urbanism, and it really struck me, having grown up in the suburbs of Houston, it just all made sense reading the tenets of traditional neighborhood design. And I happened to, while I was there, I met a guy who'd been experimenting with mass wall masonry. So after doing some other stuff and going off the Peace Corps, when I got back to the States, I called the guy up and asked if I could apprentice work, and he said yes. So I moved to the middle of nowhere, Oklahoma, Carlton Landing, and worked for $12 an hour for 2 years in my late 20s, working, doing hard manual labor. And the reason I like to emphasize a little bit about my background is because I don't have a design background. I don't have an architecture or even really an artistic background. And the reason I like to emphasize that is because the way I build, I taught myself design just by drawing buildings in SketchUp late into the evening, many nights towards the end of my apprenticeship. And I like to emphasize how simple my buildings are, how the stuff that I'm doing is not difficult, it's not hard, it's not rocket science, it's not even that skilled. I'm just building rectangles with authentic materials in good proportions. Anyway, towards the end of my apprenticeship, I had gotten in touch with another builder and an investor that basically helped me set up my first project, which I'm going to play that video for you. So this is a pocket neighborhood in Carlton Landing that we built. We bought 3 lots divided into 6 houses around a common central courtyard. And as you can see, we've got 4 structural masonry houses, and we've got 2 shingle houses that my business partner built. So this is a lime wash on the walls too, I should say. So rather than like a latex or oil-based paint, we're keeping the natural materials and the breathable paper open, lime wash on the brick. This is a moon gate in the back into a more private courtyard area. I really love creating spaces with buildings, and brick is such a good medium to do that with. So many details, like simple details like this that are easy to pull off with brick. Every brick is an opportunity to, have some shadows and interest. And we do lots of heavy timber stuff too. But anyway, I'm not going to play the rest of the video. So why mass wall masonry? To define it specifically, they all really refer to the same thing, and that's the practice of using brick or stone in such mass that it becomes self-stabilizing or self-supporting, unlike a veneer that has some kind of substructure. It's got wood frame or steel frame substructure, and then the masonry is a veneer. Mass wall, the masonry is the structure. And we do see this in the United States, some with concrete block formations and stuff. But you might be wondering, why do I care about mass wall out of all the different ways? And to me, just looking, it's one of the oldest and most resilient building practices. All of the oldest buildings in the world are built with load-bearing masonry. From the pyramids or the Parthenon to the Pantheon to the Taj Mahal to the Biltmore, all of these buildings have stood the test of time, along with entire cities that are centuries old, all built out of mass wall. And that system of building that was the product of thousands of years of human progress and evolution was essentially replaced overnight, with advent of lumber mills and mass-produced nails. And while there are obviously some great advances in building technology in the 19th and 20th century, I have some serious concerns about the durability, the health, and environmental impacts of modern building systems. And I don't mean I think we should go back in time and build exactly as we did 200 years ago. After all, most traditions were once considered modern. One way I like to say it is tradition is proven innovation. So to me, it's about blending the best of old and new. But I do think we have a lot to learn from the past, from time-tested traditions, and when I look at what is being built in the US today, I think we're missing the mark in a lot of ways. So my aim with exploring mass wall is to make buildings from authentic, durable materials that will last generations, and that will contribute to the fabric of beautiful neighborhoods, towns, and cities over generations. Just a few pictures. So this is part of the bend. This is a little 1,800 square foot house with about 60,000 brick in here. We've got these stone lintels that we'll see a little bit more of later, timber framing porches, and like I said, a lime wash, cedar shakes on here. This is just an inside. If you can see how a brick interior can be really updated and have both the combination of kind of a rough feel, but also more like a modern feel too, with the white and stuff like that.
There we go. Pretty awesome stuff. What do you guys think of that? Let's open up the syllabus and look at the weeks ahead. Here's the schedule where we're at. While we try to fix our technical difficulties. we're working on Project 1 Part B, which is due next Friday. It's the study of architectural precedent, sometimes called design in reverse. And we're trying to understand the principles and the ideas that are behind these buildings that we've been looking at. And Part B has several tasks that we need to complete. There's B.1, the on-site sketches and photos. So, if you didn't finish your perspective sketches, out in the cold because your hands froze off, use your photographs that you took and finish those perspective sketches, and then you have your details of each house. You're going to read these descriptions of Georgian, folk, Victorian, and craftsman, and submit 3 characteristics of each in a photo of each of those. And then we're going to do these size and adjacency diagrams. So selecting 4 house plans. We have some books that are up in the classroom, houses of the 20s and the teens, and so 2 of those plans need to be from like early 20th century houses, and then 2 of the plans can be from contemporary houses that you can look at from websites or books that you might have, or even a house that your firm has designed or something. Or you're going to do diagrams of those plans, and then you're going to do a spreadsheet that looks like this. So for each of the plans, you'll have the length and width of the room, the square footage. Plan A, Plan B, Plan C, Plan D, and then an average of those. So that when you design your house, you know that you're in the ballpark of how big these spaces should be. And the final part of section B is the drawings of a historic precedent house. And you have those 2 guidebooks, that the whole neighborhood in Provo that you can choose from. Any of those houses, you can pick one, and you need to do the drawings that are listed here, the sketch of the house in perspective. So another perspective drawing, make this one the best one of all. A photograph of the house exterior, a 250-word description of the house and the design. So try to avoid the word style, right? We're trying to use our vocabulary to describe the elements, the roof pitch, the proportions, the windows, the doors, the columns. What are the, use your architectural vocabulary to describe the house. And then we have the drawings that we need. In the site plan, we need 4 elevations, 3 details of the house, and analysis drawings. And this is what we're going to work on today, are these proportional drawings, so I can show you what we're trying to do. And finally, you will carefully draft and render just the front elevation of that house in watercolor at a larger scale. Questions about our precedent study? Yep.
All of that is due on Friday, or just first part of it?
All that's due next Friday. Yes. And you'll compose your drawings on a sheet, and you'll pin it up and present this precedent house to your classmates. How are you going to get the other elevations, the back elevation and the side elevation of the house that's a private house? Google? Trespass. The words, I'm an architecture student and I really love your house, can go a long way. And you can knock on the door and say, hey, do you mind if I look at this house? I'm studying architecture and I really love this house. Or you can just do your best and try to peek around the corner and get the massing from the other elevations that you have. But try to get all 4 elevations. The site plan you can get from like Google Earth or Google Maps. Right. Yeah, question?
How detailed should that elevation be something? Like overall,
How detailed?
Yeah.
Well, you can't measure it, right? Because you're not gonna get up there with a tape measure unless, yeah, you make friends with the owner and climb up on a ladder. You know, it's hard to answer that question because whatever I say will be interpreted in lots of different ways, but you're not drawing every brick. Try to get the overall shapes and proportions of it. These are at 1/8 inch scale, which is not very big. So do a reasonable amount of detail you can get at any scale. All right. No, it's fine. We're working on the computer issues. Let's see if there's anything. Let's go back here. So you also have readings that you're working on, and these are really important. It will help you to understand the principles of design that we're talking about. And they're from our assigned books from Get Your House Right and The Pretty Good House. You have chapters in here, as well as a couple of short little chapters from Stephen Sims, The Architecture of the Classical Interior, which we just provided for you. So read those, and what you do is you're taking notes as you read, and for every chapter you'll write 3 bullet points, and then at the end, just a 200-word kind of response. The questions and thoughts that this brings to your mind as you read these chapters. All right? And I think it goes without saying that we're not using ChatGPT to do any of our writing. Okay? Don't use generative AI for any of your writing. Any questions about that? Let me go to my PowerPoint then. Okay, so upcoming dates. We have the lectures every semester. If you want to take a picture of this, keep track of these dates. January 30th, April 2nd, and April 9th are the lectures that we have this semester. They're all going to be excellent. January 24th, I just found out about the STEM Career Fair. So this is campus-wide, all of the science and technology, engineering fields will have firms coming onto campus to recruit students. So if you're looking for an internship or part-time job, that's January 24th. The 3 that are highlighted in green are mandatory. You need to be there. February 8th is our all-student meeting portfolio workshop. February 27th is the career and internship fair just for the architecture program. So we'll have firms specifically for architecture from all over the country coming to that. March 18th is when the applications are due. And then just a few other dates on the calendar. March 23rd, there's an ICAA skis competition. April 12th to 13th is an ICAA stone design workshop. And May 1st is the Beaux-Arts Ball, and we'll all dress up and celebrate the completion of our hard work for the year. All right, so last time we talked about American house styles and how historians use visual characteristics to put houses into different categories. Just review a little bit what we talked about last time before we jump into the proportion. So we have craftsman, arts and crafts, Victorian or European Romantic, and Georgian or colonial. Each of these has its own history and its stylistic elements, visual qualities, and they also have sometimes other names of subcategories, right? And we discussed how these categories can sometimes overlap. Like Victorian is a really big category because it's chronological, and it's this period of history, the latter half of the 19th century. And we talked about where some of these visual features come from. That with Victorian and with arts and crafts, there was this reaction against the Industrial Revolution, and by looking back to a simpler time, right? A time when things were built by hand and with joy. And it's obviously a romantic, kind of nostalgic way of looking at the past, because the medieval Gothic period, they had no antibiotics. It was a time of plagues and no sanitary system, so it wasn't all bed of roses, right? But it's a romantic way of thinking that classical buildings were lumped into the industrial mass production. They're always the same, and they wanted something different that was made by pleasure with artisans. So we visited this house. This might be one that you sketched, the Knight Allen House. These exotic elements from areas of the world that were opening up in the Middle East and Asia were becoming available for use as precedent in houses in Europe and Utah. And it's unfortunate these houses have fallen into disrepair, and hopefully someone will come through and restore them someday. This is another Victorian house, and specifically a Gothic revival house. There's a George Brown house, right? So we saw a lot of examples on our walk. And we touched on another style at the end of our presentation last time, modernist, which is sometimes called the international style, or the Bauhaus, it's called in Germany. And this was this huge revolution in architecture. You could say the Victorian and arts and crafts were anti-classical in a way. They were chipping away at the edges of the classical tradition, but modernism was a total revolution, and it finally succeeded in toppling the giant and taking over by embracing industrialization and technology and a machine. Now, ironically, when modernism was about overthrowing the establishment, it eventually becomes the establishment. And ends up as a style as well, because it turns out it's not so easy to get rid of tradition. So one generation rebels against tradition, but the pursuit of novelty is kind of like a snake that eats its own tail, right? And we end up with a new tradition, buildings that look pretty similar over time and share a set of visual characteristics. And sadly, if we separate building style from building science, modernist houses too, they can just be turned into a costume of visual characteristics. So the same McMansion hell happens to modernism. You get the car shed, the shade tree, and just fill it with more squares. So this is what Andres Guani was talking about, how a lot of architecture has become kitsch or cliches. Another negative word is pastiche. So it's all surface and no substance, and not integrated with building science. And the last point I want to make before we jump into our proportion lecture is we need to be really careful with the definition of terms. You guys are going to graduate and go out there and be professionals, and you need to be precise with the words you use and set an example for everyone else. So people often conflate these three words, contemporary, modern, and modernist, and they don't mean the same thing. You might say a building and say, oh, that building is so contemporary. That building is so modern. When what they mean is that building is so modernist. What's the difference? Yeah.
Well, modernist would be the movement, but modern just could mean like modern day.
Yeah, modern and contemporary are chronological. They are referring to anything now. So anything that's built today, whether it looks like a glass tower or a stone cathedral, is modern and contemporary by definition because it's built today. But it may not be modernist. Modernism was a movement, like we talked about, that embraced technology and progress and efficiency in pursuit of kind of utopian dreams. So here's an example. At the time this was built, the Knight Allen was a modern building, right? But it was not a modernist building. It was contemporary with other Victorian homes, but it's load-bearing masonry and vertical proportions and pitched roofs, so it's not modernist. So today we look back and we would describe it as traditional in contrast to modernist. Both of these houses that we looked at last time, were they modern at the time they were built?
Sure.
Yes, these are modern houses for their day. But in contrast to modernist architecture, we can see the stark differences that they have. And so some would argue that this old debate between the Gothic and the classical and the Romantics, right, is not as important anymore. We could use the term classical to refer to all of this, what was happening prior to the modernist movement. I tend to agree with Leon Freer, who's the one that draws these cartoons at the beginning of each of our chapters. And he said, we don't use the term classicism as a stylistic classification. In the face of modernism, the old polemic between Gothic and classical is largely irrelevant. So that's true about our approach here at UVU. We're not so concerned about the squabbles over pointed arches versus round arches like they were in the 1800s. We're looking for timeless and enduring principles. And we've had 100 years of modernism now, so we're smart enough to not just accept everything that's trendy today as the way things have to be. We can look back and evaluate what is worth keeping. Leon Freer is famous for posing this question, is design choice or fate? Do we have to accept the style of 20th century modernism as the only option? I mean, it's 100 years old now, so it's not even new anymore. And glass cubes, frankly, are kind of boring. And I remember when we designed the Philadelphia Temple about a decade ago, the newspaper critic called it the most radical building in Philadelphia in the last half a century. So rad is rad. Traditional is radical. And especially here in the US, this is the land of freedom. Liberty and choice is a good thing. So we don't have to accept the status quo as the only fate. If you want to design a Victorian house, or a real craftsman house that's built with authentic materials, or a Georgian house, why not? This is the land of freedom. And the questions you have to ask yourself, is that right for the context? Is that right for the place? And studying precedent. So this is our approach at UVU. It kind of goes against the grain of the mainstream of architecture that's out there. But we take the past really seriously and want to study how they did these beautiful buildings that we love today. And that's our challenge, to kind of get back to basics and right this ship that's kind of capsized. So remember that design is as easy as ABCs, abstract principles, building science, and context or precedent. Otherwise, we'll keep designing buildings like this because we don't know how to do authentic traditional buildings anymore. And what will happen is cities will more and more distrust designers and architects and create historic districts that are completely frozen in time, and you're not allowed to touch or modify any of these buildings anymore because designers don't know how to do it. And then we lose all the artisans who could do brickwork and all of these beautiful crafts. So it's kind of like a double death. So let's learn the ABCs of design and avoid the double death. So today we're going to talk about one of the A's, the abstract principles, called proportion. And you may have covered this a little bit in Studio 1, but the review is good, and we'll take this a few steps further today. So this is a lecture where I try to give away all the most valuable secrets for me as a designer. what makes design really fun, because design may not feel fun. It may feel kind of like this. Not just for students, for professionals that I've worked with. A lot of people express frustration with design. When we were hiring new faculty to come and teach at this program, I would ask each one of them, what is your methodology for design? How do you go from a blank sheet of paper to your building? And most of them would say something like, well, I have to clear my mind of everything. I want to have no preconceived ideas or any other buildings that I'm referencing. And then I just start to draw and hope that I like what I see. Sometimes it looks good and I go with that. Sometimes it doesn't, and then I try to draw something else. And I just keep trying until I kind of know it when I see it. How does that sound as a design methodology to you? It sounds totally unpredictable. And there's no floor to how bad your design can be. Right? If that's all you're doing is trying to make something up out of nothing. So there are secrets that will make your life a lot easier. It's not a formula. It's not, I'm not saying it's easy, but there are tools and secrets that people knew up until your great-grandfather's generation, and then they were intentionally thrown out. They're trying to recover those principles, like the principle of proportion. If you ask most designers today how to use proportion in architecture, they will sort of stammer and stutter and will not have a clear answer. They don't really know what it means or how to use it. They know that it's important, and they might stumble upon some things now and then, but it's remarkable how much proportion has been lost. And once something is lost, we have to work to regain it. And I love this saying, speak to the past and it shall teach thee. Not plagiarize the past, not copying the past, but engage with the past, learn from the past, and it has a lot to teach us. So that's what we're trying to do at UVU. It's exciting to rediscover these principles. As a designer, it can be overwhelming, the number of things that you need to know, right? Just everything, 10,000 things. Well, you've got to have some rock solid fundamental principles as these studio projects gets harder and harder at UVU to come back to, that can give you some confidence that you're going to have consistent success in your designs. So, proportion. There's no perfect analogy, but with proportion, I like to think about chocolate chip cookies. If you ever tried to make chocolate chip cookies, you know that to get consistent results, it's the ratio of these different ingredients that makes the difference between cookies that are thin and crispy, soft and chewy, or light and cakey, or just a disastrous flat cookie blob that you might as well throw the pan away, right? If you wanted to erase traditional cooking, if you were able to gather up all of the measuring cups and measuring spoons from everyone and throw them in the garbage and have everyone forget about how to measure ingredients, that's the equivalent of what has happened in architecture. Proportion in architecture is about relationships. And I encourage you to take notes as we go. So in math or cooking or science, proportion is comparing one thing with another. So for example, both of these classical door surrounds are similar. The elements are the same. There's a 6-panel door. There's 2 ionic columns and a kind of pediment and entablature above. But if you compare the relationships between the two, what is it that's changed? We talked about Georgian style architecture. There was a variation of that style that was called federal in the United States. And a primary thing that was changed is just the proportion. So it's the same elements, but look at the proportion of the width of the door to the casing. 3:1, a much heavier proportion in Georgian, 6:1 in federal. Okay.
Yeah, they do.
Okay, yeah. We can just wait it out.
Okay. Yeah,
Thanks so much for coming. Let's give them a round of applause. So, other elements too. It's not just one proportion they changed. It's the combination of all these proportions. The ionic column is what you studied, this 8:1 canonical proportion. How about that federal column? Look at that. How stretched like taffy, the 13:1 proportion. You couldn't mix and match, interchange these different parts on top of each other. It all comes together. The proportions work as an entire system for the Georgian and the federal. Everything is either stretched or more heavy. Just like there's no one correct proportion in nature, there's a huge variety of beautiful things. So we have this iris on the left, which is a large flower on a single stem, and an apple tree, which is a whole bunch of flowers, tiny flowers, on one tree. And there's no single musical harmony that's like, this is the correct harmony. If you've ever played piano, you know that there are lots of beautiful harmonies. There's octaves and fifths and fourths and thirds, and all of these harmonies in between. And these harmonies are created in music by simple ratios. If you take a string and you divide it in half and pluck that string, it will be twice as high, twice the frequency of the first one. So that's an octave. If you take that string and you divide it into a 3:2 ratio and pluck the string, it will be a fifth on the scale. And a 4:3 ratio is a fourth on that scale. In the same way that we observe those different ratios and proportions in nature. There's not one magical correct proportion. They're relationships from part to part. Just like at the Philadelphia Independence Hall, this whole building is working under a certain set of proportional relationships, which are different from a prairie style like Frank Lloyd Wright's Robie House. You can't take these ribbon windows with Frank Lloyd Wright's proportional system and stick them on Independence Hall or vice versa. They're both beautiful, they're both masterpieces, but different from each other. They're a complete set of proportions. And when we have no proportional rules, we mix low and horizontal with tall and vertical and everything in between. We could say that this house has bad proportions. This is poorly proportioned. You can't just stick Tuscan columns on a house and say that's going to be a great house. Architects need to be able to see the problem here, which is mostly proportion. It's also probably built out of plastic mostly. Just like a face. A face can have all the right elements, but in the wrong proportion. And you know that there is something really wrong about this face. So it's actually not that difficult or complicated to understand proportion. We just need to look to nature. And the famous scientist Galileo said mathematics is the language in which God has written the universe. Geometry is that bridge between what we draw and the timeless true principles. And these tools are thousands and thousands of years old. They've been used in every culture because they are tools to create beauty. There's a certain symbolism to them in discovering truth. And we can get away from kind of arbitrary, accidental approach to architecture if we're using proportion and these principles. I love this quote: "Beauty rests upon the material thing when it has been brought into unity. And the beautiful comes into being by sharing in a formative power which comes from the divine forms." So the ancients, up until like 100 years ago, we used this term beauty. Beauty meant something. It means that this design has geometric principles that are timeless, that remind us of what is eternal. So we look to nature, we find geometry and proportion, and then we use that in our designs to make something that's going to resonate with other people, to create something that's in unity. All right, so this will be on the test for sure. My working definition of proportion. Can somebody read the definition of proportion? Let's pick at it a little bit. Yeah, thanks, Brendan.
Proportion is a design tool that makes conscious the process of relating part to part and part to whole.
Proportion is a design tool that makes conscious the process of relating part to part and part to whole. Thank you, Brayden. So all of the proportional devices that architects have come up with in the classical tradition are aids to make this easier. If you're a religious person, you can see proportion and geometry as something that reminds you of the divine. If you're not, just a secular atheist, you can still see the harmony and beauty that's in nature. And above all, I want you to see proportion as a practical tool. A tool that will take this arbitrary, kind of accidental design process and make it conscious. Your decisions that you're making. So, first principle is that proportion is about relationships, and there are two types of relationships. If we're going to avoid the monotonous grid of everything being equal, we can either have things that are closer to equal, for example, 4 to 3, or very unequal, like 8 to 1. And these are the terms that you need to know. Two things that are close to equal, we call it differentiation, and two things that are very different in their measurement, we call punctuation. Can you think of examples in architecture where you might use differentiation or punctuation? Let's say on a building elevation. Yeah.
Gothic spires would be an example of punctuation.
Okay. Okay, yeah. Let's talk about and proportion too, specifically. Yeah, I think you're right. There's kind of punctuation there. Yeah, let's dig into that a little bit more.
I was just gonna say like the cornice on like a house or something.
Yes, absolutely. I've got this tall house, and at the very top, there's an edge. Right? That's a punctuation to this overall height of the house. What other examples? Yeah, Killian.
Doorways. If you've got a facade that's got maybe 3 doorways, a good classical rules say that middle one might be a little bigger. You know, it'd be like that 4 to 3 ratio is that differentiation.
Okay, so for differentiation, yeah, we may have bays on a facade. We don't want them to all be equal. We want to create an emphasis, one in the center. Yeah.
I think similar to that could be between like the main level and the upper level, making the upper level just a little bit smaller, but same proportion like windows or something like that.
Yes. So you may have a lower level that has one height of windows. You want the upper level to be subordinate to it. Well, you can just guess Make this a little bit smaller. Or you can have a ratio and a proportion that you're using. And then now I have I've got this paneling system, and I want to create a hierarchy, and we use the same ratio. Now we're starting to develop like a melody and a harmony between these elements. So you have a packet, and we're going to fill this out as we go along, and then at the end, this is where you're going to turn in for project 1 part A. I don't know if my overhead camera's going to work. The computer problem. Could be a major issue. Here we go. Let's see this. I want to be able to show you things up here. That's not the camera I want. Hang on. Just a minute, see if I can get my camera working. Okay, I think I got it working. All right. First page. So you've got a handout at the top of the first page that says linear proportion. When we're designing, whether we're studying a precedent or we're designing our own building, how do we communicate proportion? What kind of graphic convention is there to draw? We use these two conventions in drawing to show these relationships. When two things are close to each other, this example on the left, and it's called differentiation, we use this convention. This is what I'd like you to draw there on the first page. The vertical line with horizontal lines that mark the major divisions, and then this kind of S curve, right? A sine curve. In this case, we've divided this room. There's this paneling with a molding, and we don't want that to be right in the middle of the room and divide our room in half and have this static quality. We want it to be dynamic, and the bottom portion is emphasized a little bit. So it's a 2 to 3 proportion. And we're going to use that same proportion horizontally, like Killian was saying. It has 3 bays. We want the center one to be emphasized over the 2 sides. So on your sheet, you're going to draw those curves. And then the one on the right is how we draw punctuation. It's not a curved line like the differentiation. It has these sharp 90-degree angles. And in this example, there are several divisions. Try to draw these either to the left or the right of the elevation you have there on your sheet. Take the overall height, and I want to put a pedestal, column, and an entablature in this room. Well, how tall are those going to be? I can just arbitrarily pick a height, or I can use a consistent ratio. I take the overall height, I'll make the pedestal 1 to 4, the height of the room. Okay, so 5 total parts, 1 for the pedestal, 4 for the rest. And then I'm going to take from the top of the pedestal to the ceiling, and I'm going to divide that 1 to 4, but flip it. So now I've got 1 part for the entablature and 4 parts for the column. And I could do the same for other things in the room, like my pedestal. It has a base. That's a punctuation to the pedestal. That's a 1 to 4. And then a cap for my pedestal. I'll make that 1 to 4. And we start to have this consistent system of proportions in our elevation. And so that's what you're going to draw on your first page. And then you're going to label them. So on the left, there's 2 blanks. Left one is differentiation, and the right one is punctuation. Let's see how this works in a composition by one of my favorite architects, Bernard Maybach, Palace of Fine Arts in San Francisco. Designers used to have a word for it. Some people call this the dance. We've got an overall height. We're going to place a dome on top of this big drum. But I don't want my drum, again, like, I don't want to divide it in half. I'm going to differentiate the 2. So we use a 2 to 3 proportion. And then as I start to subdivide this elevation, where am I going to make those major dividing lines using that same proportion, 2 to 3, for the top part of the dome to what's below it, the drum, and then the spring point of the arch to what's below it is 2 to 3. And notice how each time there's kind of a flipping that's happening back and forth. Differentiation and punctuation overlaid on top of that. So that's linear proportion, how parts are related to parts and parts to the whole. Let's do it with an interior elevation. I'm going to walk you through it, and then this is the next page in your packet that we'll kind of fill out together. Anytime you have punctuation, anytime you have differentiation, you can set up a rule for yourself. I'm going to follow this proportion. So here we go. We're going to start with the elevation of the room. It's a large space. The wall is the same width as it is tall, and we want to add an opening into this room. How do you decide how tall your opening is, how wide your opening is? Well, again, you could be arbitrary about it. You could do it simply based on function or code, or another tool that you have is proportion. You're always thinking about proportion. So maybe we don't want to divide the height of the room in half. We want an inflection, a differentiation. We use a 4 to 3 proportion. 7 parts for the whole height, 4 for the height of the door, 3 for what's above, and horizontally the same, 3 to 4. All right, well, how about the top and the bottom of the room? We can use that same pedestal, column, and entablature. Use our 1 to 4 ratio, which you guys learned in classical architecture. Where do I place the column or pilaster on the wall? Well, we can use our 3 to 4 ratio again. Rather than right in the middle, I can differentiate it, slide it to the side a bit. And this is where it gets really fun and interesting, is that all of the moldings, everything, all the elements in this room I can use those same proportions. So on the left is the entablature that's drawn at a scale as if it is the same height as the whole room. It has those same proportional divisions in it. And then when you scale it down, that's what's placed on top of the columns. How about other elements like the pedestal? I can use the same differentiation and punctuation, the door architrave as well, so that molding that goes around the door. Everything's proportioned in the same set of ratios. Okay, so here's our elevation. Let's see if I can switch to my overhead camera. And let's try to draw some of these proportions that we have. So this one you're probably going to want, I don't know if you have like a thicker pen or a colored pencil even could be helpful. I'm going to draw it with a thicker marker. We're just trying to get the understand the conventions of how to draw these things. So we had the overall height of the room. And we locate the top of the door. By differentiating 4 to 3. And we did the same horizontally. With this 4 to 3. See that? Where was another 4 to 3? We did our column, we located our column as 4 to 3, right? Each of these elements in your composition, we wanted to not just create this grid, we want to have some differentiation of where we put it. So that was our major moves for differentiation. How about the punctuation? What elements of punctuation did we have in the room? We had the height of the, I'll draw it over here. We had the height of the room to the pedestal. That was 4 to 1. And then we had elements of the pedestal and the entablature. Let's try that one first. So we had the entablature to the remainder. That was a 4 to 1. And then these elements in the same way, 4 to 1. Take the remainder, 4 to 1. I did the same up here. So this is a method of composition in architecture that uses geometry to generate all of these relationships that we have. And I think those are the major ones. There was another one we did, the architrave of the door, to the width of the door, and you can find others as well. Any questions about what this example is showing? Does it have to be 3 to 4 or 1 to 4? Why did I pick those? And not 2 to 3 and 1 to 8 or something? What would happen if I chose a different proportion? Right? instead of 1 to 4, what if I chose 1 to 8 or 1 to 12 as for my punctuation? What would it do?
Wouldn't it just make the elements a little thinner, kind of like the difference between the Georgian and the bedrock?
Exactly what they were doing. That's what they were playing with, right? If you wanted to change the style and look of your design, one of the things you can change is that ratio. I want my edge to be really thin. That's what modernism a lot of times did, Art Deco in the early 20th century. Just squeeze that down further and further until it's like just a sliver, right? So changing those ratios will change the design character.
Well, I have a question.
Yeah.
Do you find that 4-to-1 ratio corresponds, like, if you were gonna combine it with like a golden ratio, would you use then a 1 to 5 instead of a 1 to 4 if you were organizing maybe your floor plan with a golden ratio? I'm just curious if like a certain punctuation might line up better with like a golden ratio versus like root 2. That makes
Yeah,
sense?
that's a great question. That is where it gets really fun, is when you start to look at how different ratios can be combined. This 1 to 4 relationship is like the go-to kind of classical canon if you wanted to look very standard and like doing it by the book. Right? Different styles will show, different historical styles have their own proportional system. And so that's one of the ways that you can tell if an architect is really an expert in designing that with that style, or if they're just kind of faking it because they may have the elements there, but it doesn't have the right ratios and proportions. So you can manipulate, you can control the look of your design by changing those ratios. And that's part of what you need to study in your precedent studies to try and figure out, all right, what is the system that this architect used. So that's linear proportion. The other way of looking at proportion is geometric, primarily with rectangles. In architecture, by far, the most common shape that we use is rectangle. In plan, elevation, windows, paneling, doors, all over, right? And an architecture critic wants to boil down all of design into this pithy statement. Not all rectangles are created equal. It's literally true. And rectangles are really important that we want to understand this principle of proportion using rectangles in addition to this linear method. So, next page in your packet looks like this, right? Rectangular proportions. Is that the next page? And at the top it says a rectangle lineup. So I want you to imagine a lineup of all possible rectangles on the planet Earth and in the universe. One of those rectangles is going to be a special one. It's only one that has this property, where the lengths of the two sides are the same. So we're going to draw that one. Draw a marker so you can see better. So at the top here, we're going to have our rectangle lineup. We're going to freehand these. So you don't need to worry too much about accuracy. To the left of that square, you're going to have rectangles that are taller than they are wide. And to the right of them, of that square, you're going to have rectangles that are wider than they are tall, and they'll get progressively longer, longer. Right? And on this side, they'll be more tall and vertical.
Paul, the focus for some reason is parfait.
All right. And this is where we're going to need to use our drafting table. So I'm going to kind of switch my setup here a little bit, pull my drafting table up. So if you have a drafting table, you need to get that out. So all of you have an adjustable triangle like this. Have you ever used one of these before? So it has this little wheel on it that you can loosen it and then open it up and have Pac-Man. So you can change the diagonal. You can change the angle. What I'd like you to draw in the middle of your page here where it says proportional rectangles is you're going to draw a rectangle of any proportion that you'd like, which is not a square. Make it something other than a square. And then using your adjustable triangle, if you place the base of it against the edge of your straight edge, if you don't have that, you have a T-square, or even just at the bottom of your page, something that you know is parallel with the bottom of your rectangle. And then you can open up or change the angle of that triangle until you get the diagonal of the rectangle. back in geometry class, all rectangles that have that same diagonal are the same proportion. So if I draw a rectangle that's smaller than that one, and put the corner of it on my diagonal, I know that this smaller rectangle is the same proportion as the larger rectangle. This is one place where students often get themselves into trouble when they're using AutoCAD and they use the offset command. They have this proportional rectangle of a room or something. They offset the lines all by the same amount and think, oh, now I've got another proportional rectangle. You don't. That's not the same proportion. It has to have the same diagonal. I could make a rectangle that's larger as long as it has the same diagonal. It's proportional. So those are called proportional rectangles. And at the bottom of your page, so those are the same rectangle. You do have a command in AutoCAD called scale, which will take a rectangle and make a larger or smaller one that's the same proportion. Just be careful about that offset. Now, when we're designing something, we may not want the exact same rectangle to be everything, right? The door, the window, the plan, the elevation. We're going to create a family of related rectangles. So again, draw a rectangle of any proportion that you like here at the bottom. Just not a square. Because the square is a special and has different properties. Okay, and then use your adjustable triangle. And that diagonal is there. And I want to have some more rectangles to work with that are not exactly the same, but they're related to it. Through geometry, not in an arbitrary way, what you'll do is you have your adjustable triangle like this, right? Then you turn it 90 degrees. Place the corner at the lower right. I'm going to draw a new diagonal. This is going to be perpendicular with that first diagonal that we have. Where that line crosses the top, you can draw a vertical. And what we did is we just created a rectangle that's the same proportion, but turned 90 degrees. This one here. And that rectangle has a special name. It's called a reciprocal. And the remainder has a special name in Latin. It's called the gnomon. G-N-O-M-O.
How did you get this diagonal line for A?
The diagonal line for A, I got by taking, I've got this diagonal here with my adjustable triangle. For me, it ended up being 30 degrees. So yours might be 28 degrees or 42. And then I took my adjustable triangle and I just turned it 90 degrees. So I just rotated it 90 degrees. And then went up from the bottom. So I've got the original rectangle, the overall. And then I have the reciprocal A and the gnomon that is left over. So here it is up on the screen. I take the diagonal, right? And then the perpendicular from the bottom right corner, drop that vertical down, and I have these two created you can think of this as a family, like the original, and then the brother and the sister. Three siblings here. So this is illustrating that principle of rectangles with the same diagonal have the same proportion. This is how we found our family. We had the original, we got the reciprocal, we found the gnomon. And now think back to our lineup of rectangles to infinity. There's infinite possibilities of rectangles on that lineup. What I've done by just selecting one rectangle, finding the reciprocal and the gnomon, is now I have a family of related rectangles that I can use all over in my composition, and it gives me some choices and a variety that I can choose from. Floor plans, elevations, windows, cabinetry. So right there, if you did nothing more than just that, you have a huge advantage over somebody who's just picking rectangles randomly and trying to come up with something that just draw it until it looks right. And then they'll know when they see it. So my next question is, does it matter what original rectangle you chose? We just kind of made one up. But maybe there are some specific rectangles that have advantages over some others. We could use whole number ratios, like our musical 2 to 3, 3 to 4. And there are others that have been used in design that have special properties. So rather than just picking a random rectangle out of a hat, we have some that are special, like the square. They have special geometric properties. And we're going to draw these together. The next page that you have is called root rectangle. We're starting with the square and then doing some that are geometrically related. Okay, so set up your next page, the root rectangles. Well, all right, let's start with the square, and to not get so large that it expands beyond the reach of your compass. Probably you can do this at about like a 2-inch by 2-inch square, or maybe 2.5. So get your architect scale, probably like a 2 by 2 or 2.5 inch square will work for you. the diagonal of the square? What angle is it? It's gonna be a 45, so I can construct my square here. I'm going to give these sides the length of 1. As we draw these rectangles, they're all going to have the same base. So that bottom line, we're going to extend that out to the right. And now you'll need your compass. So I'm going to take my compass. And make the length of that thing the diagonal of my square. So place the point of the compass at the bottom left, the pencil at the top right. And then draw an arc down until it crosses our baseline. And that's going to be the edge of our next rectangle. These are going to be different from the whole number ratio, the 2 to 3, 3 to 4. They're irrational numbers. Anyone tell me what the length of that side is going to be? Remember back to your Pythagorean theorem, a squared plus b squared equals c squared. Does that ring a bell? So we have 1 squared plus 1 squared equals c squared. So c is going to be what? The square root of 2. Which is what? Somebody look at their calculator. 1.4. Can someone give me a few more decimals? 1.4.
1.
It keeps going, right? 1.414. It's an irrational number. It never ends. It just keeps going. Well, that has a diagonal to it. So I can open up my adjustable triangle. What angle did you get on your adjustable triangle? About like 34.5 degrees for that one. Open up your compass. Now to the length of that diagonal. And you'll drop that arc down. That's the new outer edge of our rectangle. And what's that length going to be? So we have 1 root to the square root of 2. Now we have 1 squared plus square root of 2 squared equals 3 squared. So that new length is going to be square root of 3. Square root of 3. That has a diagonal. What did you get for that diagonal angle? When you get there, tell me what that is. So it's a square root of 3, which is 1.732 dot dot dot.
Better be 30 degrees.
30.
Did you get 30 degrees?
Yes.
If you did, then you've done your drawing accurately. Congratulations. So our original square had 45-degree diagonal. The next one was about 34.5, 35, and the square root of 3 is 30 degrees. So there's a reason why when you get your set of drafting tools from the bookstore or Amazon, that it comes with a 45-degree triangle and a 30, 60, 90 triangle. In drafting, that is this root 3 rectangle. It was the whole proportioning system for the Gothic period. How they designed all of those cathedrals using a 30, 60, 90 root 3. Let's do one more. Maybe 2 more. So if we have 1, then it's the square root of 2, then it's the square root of 3. Anyone want to take a guess what the next one will be? Square root of 4, which is equal to what? 2. So we just found a double square. It's kind of remarkable. We're in this irrational world of all these numbers that aren't real numbers, and then eventually we get back to the rational world. Square root of 4 equals 2. And what's that diagonal? Around 26, 27. I'm starting to lose accuracy because I've got this fat pen, but if you do it in with really precise instrument, if you do it in AutoCAD, you can do the same drawing. Every time I design something in AutoCAD, I have all these diagrams off to the left. I have my proportional rectangles right there that I can scale and I can use in composition. So we have 1, square root of 2, square root of 3, square root of 4. Now, we're getting rectangles that are longer and longer that would fit on our lineup of rectangles to infinity. The square root of 5 is about the last one that you'll ever find in like a proportional system. Because beyond that, can you imagine like as a medieval or Renaissance architect getting out your compass and doing this over and over and over after about 5 times? It's not going to be very accurate anymore. So these rectangles, square root of 5 was about as far as you would get, and then you would just add rectangles together if you wanted to get a different proportion.
You also run out of length on your compass. They don't make them that big. I've tried.
Yeah, you got to get extensions for your compass. But one more that we do want to find is the golden ratio. And the golden ratio we find by the, it's called the semi-diagonal. of our original square. So we're going to we're going to find the center line of our square. So divide our square in half. We take the two diagonals, they're going to cross right in the center of our square. And my compass is too big. So this is called the semi-diagonal. That's the opening that you from the bottom, middle of your square to the top right. And you'll drop that line down and it will be in between. Right in between the root 2 and the root 3. So we need to squeeze another one in there. That one right there. We have 1.414, 1.732 on the other side. It's a symbol like this in Greek. We call it phi. And that ratio is 1.618, etc. I'll give you a couple minutes to finish up that drawing. Anybody get stuck? Anybody have severe geometry problems that need help? These are the root rectangles.
Don't say yes. Yeah. Trick question.
Yeah, quick question. Were these used so frequently just because of their ease of tool use using a straight edge compass? They didn't require like standard measurements. Does that make sense?
Yes, I think that was part of it. You can generate these if you're illiterate. If you just have a set of tools. If I have a compass and straight edge, I can make all of it. They also have some special geometric properties. Just like in music. Does anybody play the piano? Play the violin? Right. You'll notice that certain intervals of notes create harmonies that jive well with other intervals of notes, and other proportions of clashing and dissonance. If we're trying to come up with rectangles that are going to play nicely with other rectangles in a composition and work out for something that doesn't leave us with weird, awkward slivers at the edge and things that don't add up. The golden rectangle is pretty amazing because it's the only one. All of our compositions, you're probably going to include squares as well. And the golden rectangle is the only one where you can take that rectangle, remove a square, so divide it with a square, and then what's left over. And what's left over is the same proportion as your golden rectangle in the beginning. No other rectangle works that way. They all will end up with a different proportion, and then you can't have this harmony again and again and again at smaller and smaller scales. So another answer to your question is they kind of work like magical harmonies as you're trying to compose them. So that's what's special about the golden rectangle. What's special about the root 2 rectangle? If you've ever been to Europe, they use different sized paper than we do. You ever notice that?
Mm-hmm.
We use 8.5 by 11, 11 by 17. They use A0, A1, A2. Why do they do that? Because those are root 2 rectangles, and root 2 rectangles are the only ones that you can divide in half, and both of those are the same proportion as the original. So you can enlarge something 200% or shrink it 50%, and all the margins end up the same on your paper. Which doesn't happen with 8.5 by 11 and 11 by 17, drives you crazy. Now you got like weird borders on your page. That's why the root 2 rectangles are special, and it's the proportional system that was used in Romanesque architecture throughout history. So if you want to design a Romanesque revival building, you're going to use the root 2 proportional rectangle. I mentioned the root 3, the 30, 60, 90 triangle that makes up our equilateral triangles, right? That is the proportional system for the Gothic. If you want to do a Gothic revival house, you better get out your 30, 60, 90 triangle. And it's related to that Vesica Pisces shape that we drew. You look at, if you study Gothic cathedrals, plan, section, elevation, rose windows, the shape of the piers and plan, all of them are this 30, 60, 90 root 3 rectangle. So we're here in Utah. So forgive me if I use an example of a temple here. Truman Angel was the designer of the Salt Lake Temple, and analyzed this elevation. I used to work in Salt Lake City at the church office building and give tours of the Temple Square, and people would ask me, what style is that building? People would come in from out of town, they wanted to know what style it is. And it's kind of a tricky question to answer. There's a lot. You could just use the default, well, it's Victorian eclectic. Right? It's a little of everything. But maybe proportion can help give us some clues. Truman Angel was a carpenter. He worked as a construction foreman. He was not a trained architect, but he learned the tricks of geometry and proportion. So how did he proportion the elevation of the temple? Let's pull out that sheet. It's the next one in your packet, right? Or do we have another one before that? We have one. We've got the whole number of musical rectangles. Let's throw those quick, and then we'll come back to it. For these, we're going to introduce our magical tool called the proportional divider. Just want to get a proportional divider around and may have that. There are different companies that make these. They don't always come with the same features, but probably if yours is somewhat similar to mine. On one side of it, it says circles, and on one side of it, it says lines. Maybe you have to flip it over and find that on the other side. So the circles and lines. The ones that say circles are meant to divide up a circle into a certain number of parts. We're going to use the one that says lines. And you'll see, like mine starts at 10. Does yours start at 10? 10, 9, 8, 7, 6, 5, 4, 3, 2, all the way down to 1. So I can actually use my proportional dividers. What you need to do is close them so they're both aligned. And then you can unlock it with this wheel, and you can slide that die up and down. Slide that mark. And you're going to slide it all the way down until it's lined up with the number 1. And you'll lock it. And once you lock it, you can open it back up again. And whatever size you open this to, the distance on the left is going to be the same as the distance on the right. So it's a 1-to-1 ratio. So I can draw my square here using proportional dividers. So top left is the square. I know that I want the two lengths to be the same. So I open up the proportional dividers on one end, and put them, this is kind of a silly way to use these proportional dividers. Those are easy on the other rectangle, those are easy ones. All right, so that's my, that's the height. That's going to be the same as the length. For a double square, instead of a 1-to-1 ratio, it's 2-to-1. So I take the proportional dividers, you gotta close them again to change the division. And loosen up the dial, slide it up until it's lined up with the number 2. And now, every time I open this divider, these distances have a ratio of 1 to 2. So the larger one is twice as wide as the smaller one. So if I have a given length for the base of my rectangle, right? And I know I want the other length to be 1 to 2, half as tall. I can use proportional dividers. And now I've got a couple of different techniques, right? We found this with our compass, making those 2 rectangles. We can also use proportional dividers. Find the same proportional rectangle. These I'm calling musical rectangles because they're related to the musical scale. We look at the piano, how it has an octave, a 2-1. So that double square, you could call it the octave of the first square. And at the bottom we have the 5th and the 4th. The 5th is a ratio of 3 to 2. If you're really lucky, you've got an old pair of proportional dividers that actually have little markings on them. Let's say 3 to 2 and 3 to 4 and the golden ratio. Does anybody have that marked on there? If you don't, then we're going to have to find those. They're going to be in between the 1 and the 2. So what we're going to do is we're going to measure it. So draw a rectangle using your use your architect's skill. 3, and then the height would be 2. I'm going to measure it because my proportional dividers came from Amazon. They don't have this marking on them. Sadly, so I need to find it because this is a really useful measurement. It's our musical fit. And how am I going to find it? Well, the 3 to 2, I will tell you, is a little bit more than, it's not quite halfway between 2 and 1. It's a little bit closer to the 2. And I'm going to do it by trial and error. So I'm going to lock my proportional dividers about where I think it is and check 3 to 2. There it is. When I found it, then I can take a Sharpie. There were some Sharpies back there, and I can mark that on here where 3 to 2 is. And then do the same thing for your 3 to 4. So draw a rectangle that's a ratio of 3 to 4.
The sign is it all the proportional dividers between 1 and 2 for the very first one?
Yeah, they're both going to be between 1 and 2. So I want you to find those on your proportional dividers. And then I want you to also find the diagonal. And what that angle is. You'll notice that the 4 to 3 is a little bit more squarish than the 3 to 2. And then check your adjustable triangle, find the angle for both of them. Or 3 rectangles, about 37. And the 3 to 2 rectangle. 32 and a half. So you've got an arsenal now. You have musical rectangles, these whole number rectangles, and you have the root rectangles. What's nice about the whole number rectangles is they're measurable. If I'm laying out a room in a house, and I have it 12 feet by 8 feet, right? That's a whole number ratio of my 3 to 2, and that's pretty easy for someone to measure and lay out. If I'm using the root rectangle, it's going to be an irrational number and end up with some kind of crazy measure in reality when I'm building. Yeah?
How did you do the fourth
Which one?
one? The fourth?
If your proportion dividers come with that on it already, then you can use that. If it doesn't, then you just measure it using your architect scale, find the scale on there that will fit on your paper, and do a rectangle that's a ratio of 40. Does that make sense?
Yeah.
Okay, then once you've got that, let's come back to our upright temple elevation. And this is the last exercise we'll do, and then you'll just scan all your drawings and upload them to Canvas for this assignment, okay? Let's see if we can design this thing in reverse. You can set your elevation on your graphing table. And let's first see if we can find a proportional rectangle for the elevation. This is what you're going to do with your present building. You're going to try and see if you can decipher what the proportional system is. So we need a nice heavy line at the base here. We have a horizon line. And it may take some trial and error using your proportional dividers, using your adjustable triangle. I know from past experience that Truman Angel designed this as a Gothic revival building. So what proportional system was he using? The 30, 60, 90. So open your adjustable triangle there to 30 degrees. And you can see that this building actually fits, so draw a line at both outer edges. And if you take your adjustable triangle and move it 30 degrees, the diagonal of this elevation rectangle fits perfectly in the root 3 or 30, 60, 90 triangle. I can draw that same diagonal from the other side. And I don't think it was a coincidence that where those two lines intersect is right in the center of the inscription that describes the purpose of the. And we can check and see if that was consistent with how we designed other elements in the facade. So let's take this window right in the middle here. And use that same diagonal. Remember, rectangles that have the same diagonal are the same proportion. The window right in the middle is 2 root 3 rectangles stacked one on top of each other. If you check other windows, you'll find that they're similar proportion. Is everything a root 3 rectangle in this elevation? No, but that's an overall organizing proportional system. And remember, we call that geometric proportion or proportion of rectangles. Remember what the other system was called, the first one we looked at? We did rectangles, and we did, we called it linear proportion, right? We did the differentiation and punctuation. Let's take this centered tower as an example of something that it needs to be subdivided. If I'm a designer, I've got this center tower. It's going to go straight up for a while, and then at some point, it's going to start stepping and tapering in to a point. Well, where? At what point on this tower do I want that to happen? That's a ratio of differentiation. So if we draw a straight line going up on the side of our page, this point right there is where the Truman Angel decided, okay, I'm going to stop being vertical and I'll start being at an angle. So we can use our differentiation diagram. Remember how we did that with this curving line? And now we've got a remainder at the top. If you remember how Bernard Maybach designed the Palace of Fine Arts, use that same ratio, that same proportion to determine the next regulating line of his tower. So how many times does this tower step in? Here's one, it starts to step in, here's another, and here's another. And we can see that they're not all equal. He didn't just divide it into thirds. He's using some kind of proportional system. If we pull this one across, he's differentiated that, and then the next one, similarly. flipping it upside down and doing what designers call it the dance, right? I have a ratio, I'm gonna use that, invert it, keep repeating that ratio, so the whole composition has a rhythm to it, has a cadence. That's not arbitrary, it's all generated by a proportional group. So we found 30, 60, 90, we found all of these differentiations. And as we get into design, it may feel a little bit new, it may feel a little bit awkward at first. It's just like if you've ever learned a musical instrument. Your teacher forces you to sit down and play scales. And you're like, why do I have to play scales? I just want to play music. But it's in practicing those scales you realize 2 or 3 years down the line that you've developed an ability to hear all of these harmonies, and music is a lot easier. So as we're designing this house, and especially the third project for the semester, project 3, which is a larger house and has these grander spaces where we're thinking about volume. This is how I'd like you to approach, and your studio teachers are going to encourage you. I won't say force. They will encourage you to use geometry and use proportion in your design, not just making it up. Because if you're using geometry and proportion, you will find that you're able to relate the part to part and part to whole in a really beautiful, complex, geometric, and harmonic way. So this is the last slide. There's a special word for this in Latin that comes from Vitruvius, and this may also be on the test. It's called taxis. Not taxis, these are not the yellow cars you find in New York City. This is taxis in Latin, and taxis means ordering the floor plan. So it divides the building into parts and establishes logically organized divisions of spaces. You're going to have a lot of rooms, a lot more rooms than your around or even have to work with. How are you going to fit these things together in a logical way that's not just a bunch of random shapes? Be deliberate about it, be thoughtful about it, use geometry and use proportion, and then you've got some tricks and some tools. The last page in your handout is extra credit. If you'd like to take these tools and try to design a little building, I'm going to give you the program for this building, okay? It has 3 spaces. The main space is 1,600 square feet and has 2 ancillary spaces of 400 square feet. So 1,600 square feet in the center, 400 square feet on either side, and you're going to draw a plan. And then above that, an elevation, and you're going to use these tools, proportional rectangles, linear proportion, and design a little floor plan and elevation. For some extra credit, if you want to do that, and then you can bring them with your package. Happy to take any questions before we go? Everybody good? Okay, so Monday you're meeting at your regular time with your regular schedule instruction. So I'll see my class at 9 a.m. on Monday.
You mean Wednesday, Paul?
Yeah,
Wednesday. Yeah, Monday's a holiday. I won't